Hey there, everybody. Mr. Carlson here, and we're going to talk about equilibrium in today's video. Equilibrium. Equilibrium is when we have essentially forces that balance each other out. So we've kind of already talked about this when we were learning about Newton's three laws. But whenever I have a net force, and remember, when we're talking about the net force, we're talking about the sum of all the forces acting on something. Whenever the net force is zero, that means we refer to that as equilibrium because it's not accelerating. So if I look at this example right here, right? I've got this box. I've got two guys on either side pulling with an equal amount of force. So the left guy here pulling with 10 newtons this way, the right guy over here pulling with 10 newtons this way, and so therefore they just cancel each other out, because again we can think of maybe this is negative 10 newtons here, this is positive 10 newtons, and so the sum of those two forces would just be zero. And so we say that and the box doesn't accelerate, and so therefore this is in equilibrium. So now let's take what we've been talking about with vectors, and let's say we get a situation where we've got two forces acting on this box which are not canceling each other out. So let's say that we have an example where that net force is not zero. If that happens, what we can do is we can apply a force to that in order to get it to stay in equilibrium. So for example, let's take that same box from up here at the top, and it still feels a force of 10 newtons this way, but let's say now it feels a force of 5 newtons in this direction, so at 90 degrees. So we'll say 10 newtons is at 180 degrees this way, but now there's 5 newtons of force at 90 degrees this way. So if I just left it like this, and this box is feeling those two forces and nothing else, well then the box is definitely going to accelerate because there's no force balancing out this way, and there's no force balancing out in my vertical direction. And so this box is going to accelerate somewhere like this way, right? Our resultant force here, our resultant vector is going to be somewhere in this direction. And so that box is definitely going to accelerate this way. So what we can do is we can put what's called an equilibrant force. An equilibrant force. Let me write that up here actually. Equilibrant force, which is basically something that's going to balance out one force that will balance out this and keep it in equilibrium. Keep it in equilibrium and keep it from accelerating in that direction. So let's think about this. If I right now, let me get a different color here actually. If I think about this in what we've been already talking about so far, we would get from this, adding these two vectors up, we're going to get a resultant vector, right? That is something like this. It's going to be in this direction, like so. We're going to label that R, our resultant force. If I want to balance that out, well, essentially what I need to have is something that's exactly in the opposite direction, going this way. So these two forces added together, right? These two things added together are going to give us a resultant force that is this way, which means the box is going to accelerate in that direction at whatever net force that is. And so if I want to balance this out, if I want to have an equilibrium, if I want to have an equilibrant force, it's going to be exactly opposite of my resultant of these two vectors, right? So I'm going to get a different color here. And so our equilibrium force, or our equilibrant force, is going to be like this, in the exact opposite direction this way. And also, not only is it going to be the exact opposite direction, we know that the direction has to be completely opposite, but also it has to be equal to whatever this force is. It has to balance it out. So this force here, I'm just going to label this E for equilibrium. This force E here has to be equal to R and opposite in the direction in order to keep it at equilibrium. So this force E here has to be, we'll say, equal in magnitude to R, but opposite in direction. Opposite in direction. So what I want to do in this problem then is figure out, well, what's the force that I need to apply and in what direction? What's the amount of force that I need to pull this way, and what is the exact direction that I need to pull in with that force in order to keep this box at a state of equilibrium and keep it from accelerating in any direction? So the first thing I need to do is, using what we've already learned, and come up to this part right here, and I need to figure out this first, because if I can figure out what is the resultant vector here, well, then I can just say I know what the magnitude is going to be in this direction. So the first thing I need to do is figure out what's my resultant force. And we know the process for that. What we're going to have to do is we're going to have to take either this vector here or this 10 Newton one, and we're going to have to move one of them so it's from tip to tail. And so I'm going to take this 5 Newton vector here, and I'm going to move it this way over here. So it's tip to tail. Move it like that. So now I've got the tip of my 10 Newton vector connected to the tail of my 5 Newton vector. And the reason I want to do that is because now, along with my resultant here, I have just made a nice, neat right triangle. And so now I can use some trigonometry to solve for what is the magnitude of my resultant vector, which is going to be r is equal to the square root of 5 squared plus 10 squared. Crunch the numbers on that, and we're going to get a resultant vector of 11.2. 11.2 newtons. Now that's the magnitude at which this force is. So this force is 11.2 newtons. Now that means that this magnitude of this force, my equilibrium force, also has to be 11.2. 11.2 newtons. So I know the magnitude, but I'm not done, because I also have to figure out, well, at what direction do I apply that force? Or in other words, what's the angle at which I have to put this force? What is the angle that I have to put this force on this box in order to cancel this out? Because I can't just apply 11.2 newtons in any old direction. I can't just pull with 11.2 newtons this way, because that's not going to balance it out. I can't just pull this way with 11.2 newtons. It has to be in an exact specific spot or an exact specific angle in order to cancel out this 11.2 newtons. So the first thing I have to do is come back up to this triangle here, use my trigonometry to figure out maybe this angle first, and then from there I can figure out what angle do I have to put this force at. So again, using our trigonometry here, so I'm just going to use the sine function here. So the sine of, so this is angle theta, the sine of angle theta is equal to our opposite side over the hypotenuse. Our opposite side over the hypotenuse. So sine angle theta is equal to 5 newtons over 11.2 newtons. So that means I just have to take the inverse sine of 5 over 11.2. Let me do that in my calculator right now. So 5 divided by 11.2 inverse sine, and we get angle theta is equal to 26.5 degrees. So this is right here is 26.5 degrees here. Now, how am I going to use that information to figure out the angle at which I want to place this? Well, let me just put in a coordinate system here real quick. So this is, remember, this is our 0 degrees. And then going up from here, this would be 90 degrees. Then going over here, this would be a full 180. And then if we go to this would be 270 degrees. And if we made it all the way back around again one time, right, would be at 360 degrees. So really what I want to figure out is I want to figure out this whole to here is what I want to figure out. That's the angle that I need to apply this force, is this angle right here. So starting at 0 and working my way till I hit this, that's the angle at which I want. Well, this is 26.5 degrees. That means this distance from here to here would be 180 minus 26.5. So punching that in, 180 minus 26.5. That means this is 153.5 degrees, which means that this distance from here to here, so from 180 to my equilibrium force here, that's also 153.5 degrees. And so all I have to do is add that all together, right? 153 plus 26.5 plus another 153.5. So let me do that. And we get 333.5. So that is going to be the angle. So from here all the way around to here is 333.5 degrees. So my equilibrium force, my final answer here, equilibrium force, we'll say, is equal to 11.2 newtons at 333.5 degrees. And that would be my final answer for that one.